and about the autonomous aerial vehicles, and also talk about the trajectory control of aerial vehicles and define the problem. And then we go through the nonlinear NPC. Go through the nonlinear NPC and how to design the objective function. Also go through the implementation and design of the NPC in MATLAB using CasADi toolbox, and also what are the stability conditions for the NPC. Then go through the real-time implementation on ROS, and finally look how to extend the NMPC for learning-based models. So first of all, like for autonomous aerial vehicles, now they are very popular in like civic and military applications, and we can see them like in secure and search and surveillance, and also for inspection due to the simple configuration of the vehicle, and also its system is agile dynamics, and also there's limited maintenance requirement plus the low safety requirements. But on the other hand, there are some challenges in the design of the control of the aerial vehicles, which is the system is underactuated. We have 4 inputs and 6 outputs, or 6 degrees of freedom, and also the system is open loop unstable. Then the system had 3D nonlinearities invoked by the rigid body dynamics of the system, and finally the payload constraint that limits the computational resources and sensors on the vehicle. Some techniques or some controllers proposed in the literature, they were able to address the nonlinearity of the system, but there are some major drawbacks that they can't address. One of these drawbacks is when the vehicle moves like with aggressive trajectory, or there are sudden change or sudden turn in the trajectory of the vehicle. So what happened that for other like traditional system, when the vehicle goes in a straight line and it doesn't know that it should turn left. So what happens? There will be a jump happens here, or overshoot happens in the trajectory, because the drone or the vehicle doesn't know that it should turn left unless it comes at this point. But on the other hand, like we could design the system, and we can help the drone to look into the future, look a step ahead. And for this one, the drone knows like ahead, it should turn left, so it will smooth the trajectory before it reaching there. And we call this one moving horizon controllers, or also as known as model predictive controllers. So for model predictive controllers, we have the model, we have the controller, we take the error from the reference and the feedback, and then we apply the control input, generated control input to the system. So the advantage of this model predictive controllers, that it can predict the future state using the system model. Also, it can tackle the input and the state constraints. For other traditional controllers, they can't implement the or controllers other than optimal control, they can't implement the input and the state constraint in the system. And in this case, they have to add some saturation after the controller to limit the input going to the system. But this issue that the controller is not aware of this saturation if the control input goes beyond the threshold. But for MPC, we can impose the input and the state constraints in the system and take it into consideration. Also, it's applicable for multiple input, multi-output systems. So now, since we have using model predictive control, we need a model. We have to find a model of the system that we are after here. So in this case, we have to design the mathematical model of the vehicle or vehicles. So in this case, we have two frames. The first frame is the global or initial frame, and this one is fixed like as a reference for the drone. And we have the body frame attached to the body of the vehicle, and this one moves as the drone moves. And we can relate the body frame to the global frame using the position and rotation of the vehicle. And then to find the model of this vehicle, we have assume that the vehicle is moving in this direction. So in this case, we have the thrust, the collective thrust of the four rotors will be pointed at this direction, and then we can project the thrust in the two axes, and the vertical one will tackle the width of the vehicle, and the horizontal one will tackle the drag force applied by the air or applied on the system. So we can resolve the thrust on this direction. So in this case, our forces are expressed in the global frame, or we can project the weight. So our forces are expressed in the body frame. So to go to the model, like we have the status-based model or nonlinear status-based model, and this one had the states X and the inputs U. And for this one, we have the kinematics of the position, which is we have the velocity expressed in body frame. Just we transfer it using rotation matrix to the body, the world frame or global frame. And then we have the dynamics of the velocity that includes the thrust, the force of the thrust, the force of the gravitational weight, and also the force applied by the drag force. And here the force applied by the drag force is linear or proportional to the speed of the drone. So as the vehicle moves fast, we get like higher drag force, like to resisting the motion of the vehicle. And then like you have the position and the velocity. And as we talked before, that the system is under actuation, so it means we have number of control inputs that less than the number of degrees of freedom. So in this case, it's better to deal or treat the control system as two loops. The inner loop here, it considers or takes into consideration the attitude dynamics of the system. Since the attitude dynamics is decoupled from the rest of the system, so we can design the inner control loop and using, for example, PT controller, we can stabilize the system at very high rate controller. And for this controller, it generates the required torques and thrust going to the drone, but it needs the commanded angles. Like it means the commanded angles or commanded attitude that it should follow using this controllers. And this is the objective of the outer loop control. So the outer loop control, we here designed the NMPC to design the trajectory tracking for the system. And for this one, it generates the required thrust and generates all the required attitude angles going to the inner loop. So in this case, in order for the NMPC or the controller to control this system, it should be aware what is going inside this block, the orange block. So inside this orange block, we have to model the controller. So if we say that in most like common commercial and research controller drones, they come with built-in controllers. So if this controller is a PT controller, so in this case, we can design the inner loop as a simple first order PD controller. And in this case, if we know the parameters of the controller, we can directly get the gain and time constant, which are the key and tau of the controller. If we don't know the values, we can do simple system identification to identify the system of the inner loop. Once we have this model, it means we have the model for the outer loop of the system. And in this case, we have the rod angle, pitch angle, and yaw angles are the angles of the attitude dynamics. And we have the states and we have the inputs going to the system, which are the commanded commanded roll, commanded pitch, and commanded yaw. And as we can see here, the commanded yaw or the dynamics of the yaw is simple nonlinear system, so it doesn't affect or is decoupled from the rest of the system. So we can either include it in the MPC design or we can exclude it from the MPC and use it like P or PD controller. We can stabilize the yaw angle. So in this case, we have the 4 inputs to the system coming from the outer loop, which are the thrusts and the 3 commanded angles. Then now let's go forward to the design of the MPC. So for the MPC, it's like playing a chess. For playing a chess, the player like makes a plan in his mind for some steps ahead, like for 3-5 steps ahead to win the game. So he makes his plan and applies only the first motion. And based on the response or based on the play from the other player, he like starts to adapt his plan and like based on the inputs coming from the other player, and then apply like a new plan and apply on the first play and so on. So this is exactly what happens in the MPC. So for MPC, we have the this is the, for example, time frame, and we currently at this point, which is point K. And for this point K, we have the capability to look ahead for a certain prediction horizon or prediction window. We call it N, number of steps ahead. And we have the sampling time of this discretization of this system. The sampling time is important because it defines the time window of the prediction. If the sampling time is very small, it means we have a small window of time. If the sampling time is large, it means we have larger window. So it depends on the application itself. If we have faster system, so it means we should be having a small prediction horizon, small time sampling time. If we have a slow system, for example, chemical or process system, it's okay to have large sampling time. Okay, so in this case, we have this reference trajectory that we would like to follow. And for the MPC, it plans ahead in its mind, like it plans the open loop input. So it says that if we apply this open loop input, we should find that the trajectory of the system or predicted state should converge with the reference trajectory at some point. So this is hopefully the plan that we are making. But when it comes to reality, once we apply only the first control input of our plan, we figure out that the actual response of the system is like diverged a little bit from the actual one. Sometimes it's okay to converge or to match the plan, sometimes it's not. And this is because there are some unmodeled dynamics applied in the system, there are some disturbance applied in the system, and there are some other factors that may affect the performance of this controller. So in this case, we have the response from the controller. So it's a planet. So in this case, we can consider the microcontroller and the controller as a first player and the planet as the second player. Now I play against the planet. So in this case, I have to adapt my plan again, like using this initial guess. I have to adapt my plan again, and in this case, we plan like we have another open loop, like a new strategy, and this one tells us that using this condition we should converge at certain point as well, and then we apply only the first control input at this point, and then we see how the response and so on. Okay, so this is the idea of the model predictive control in general. So in order to design the open loop control, we need, or the open loop input, we need some criteria. So what are the criteria that we should follow to generate this input? So this criteria can be defined using the cost function or the objective function of the system. So for this cost function, it starts first with the defining the running cost. The running cost is one time, like a cost at one step, like for the k plus one and so on. So for this case, and like in this case, we have the L, which is the running cost. It contains the penalization of the tracking error, which is the difference between the predicted and the actual the reference trajectory. And also we have the penalization of the input, which is the difference between the open loop input and the reference input. Sometimes the reference input is just 0 because we would like to minimize the control input. Sometimes we have some value for the reference, or sometimes we have some values for the input. So we can include this reference value of the input. And we have Q and R are just weighting matrices, like the LQR control to penalize or give some priority for the tracking error or the control input. So here we have the value of the first term, which is the tracking error, and second term, which is the input tracking error. And then once we have the one value function, cost function, so we can design for the entire prediction horizon. So it means we get the cost function and we start get it for the entire in prediction steps. And then we keep moving. So it's called the moving horizon. So at each time we move and we start a new prediction horizon. So in this case, we would like to we have the running cost at all the stages, or at all the steps. So to get the optimal control value, we'd like to design the optimal control problem. So the optimal control problem here, we designed this one using the objective function, and the minimization of this optimal control problem leads to the optimal control sequence or the optimal control input. And in this case, we have our objective function, and just we minimize, like we find the manipulated variable, which is u, to minimize this cost function. Once we find u, it means this will be the minimum value of this cost function. And this cost function, sometimes like we have to consider some constraints in this cost function. The first, or this optimal control problem, the first one is the system dynamics. We have to make sure that this prediction should constrain or should stick to the physics of the system. So it means we have to respect, or to have to follow the system dynamics of the system. So any prediction should follow the system dynamics. Also, we have the initial step of the controller, or initial step of the prediction should include the actual initial position of the current state of the system. And also, if we have some constraint in the upper and lower limits of the control input, we can apply it also to the control problem. Also, similarly for the states, if, for example, you have like some constraint on the boundaries or the arena that we are working on, so we can constrain this one using some state constraint applied to the system with upper and lower limits. So now we have our MPC block. Now we should know like what is inside this block. So inside this block we have the optimal control problem that we have designed before, and this optimal control problem includes the constraints and the cost function, and also we have the prediction. So using the feedback, we can apply to the system model to predict all the future steps, or all the future states using for the prediction horizon, and then using this prediction states we can calculate the error and inject it to the optimization problem, and so on until we do the optimization and end up with the control inputs and apply only the first control input to the controller, then they get the feedback and so on. And this is the loop of the MPC. So to implement MPC, like the coding of MPC or implementation, so there are some multiple toolboxes available. The first one is MATLAB built-in MPC toolbox, so that we can use it to design the problem. But in this case, we have the generic quadratic problem of the MPC, but we not allowed to modify for a specific forms or a tailored objective function, as you will see later. Also, we have the MATLAB fmin function, and this is minimization optimal control function. But this one is a little bit slow in real-time applications. And also we have CasADi and CasADi. They are open loop toolboxes available online that we can use them to do real-time implementation of the MPC. In our case, we selected the CasADi because CasADi is a symbolic framework that we can use it to design a symbolic problem of the MPC and then apply it to the system. Also, CasADi is open loop toolbox for nonlinear optimization, so it's perfect for the nonlinear problem that we have. Also, CasADi facilitates the rapid and efficient implementation of the numerical optimal control problems, including MPC. Also, CasADi is compatible with MATLAB, Python, and C++, so we can use it in any of those platforms. So that's why we selected CasADi in our study. So in order to do the implementation of the MPC, we started first with the optimal control problem that we have. We have the objective function and we have all the constraints applied on the system, but unfortunately we can't apply this one in coding directly. We have to convert it to some other forms. So the objective of this one is to find the desired or the optimal control sequence. In order to do this one, we have to go through some in between intermediate steps. For example, to convert this problem to nonlinear programming problem. So we have to find numerical representation of this optimal control problem, which is NLP, or which is the nonlinear programming problem. So in a nonlinear programming problem, it's similar to this one, but we have the objective function. We have a function. We would like to minimize this variable, and we subject to inequality constraint and equality constraint. So we have two kinds of constraints, equality and inequality constraint, and then we can code this function or implement this function in the coding. So in order to go in this way, so we have to find something in between. So for example, like to do this discretization, we can use something called single shooting discretization. But for single shooting discretization, we consider only the U as the input, the U as the decision variable. And in this case, we have to solve this constraint for the entire prediction horizon. So it means we have the initial condition x0, and then we have decision variables u for the prediction horizon. So we take the first u with the initial condition, apply it in the system, and then we do the integration to find the first value of the state corresponding to this constraint. Then use the whatever we get from the states, use the second value of the input, and do another integration to find the next state, and so on. So it keeps propagating of the integration, which is very computationally efficient and inefficient in designing the MPC in real time. This is why it's not like desirable to use the single shooting. The other one is to use the multiple shooting. For multiple shooting, we deal with the system as lifted single shooting. So we have like bunch of single shooting. So in this case, we have the u and the x are decision variables, and each time we find out each prediction step, we have a value for u, a value for x. We plug them in the system, and here we have that we can see that f minus x is 0. So this is our constraint. So in this case, we have f minus x is 0. But this x is the initial condition, and this x is the next one. So if we have two columns, one decision variables for u, one decision variable for x, if we take the first u, first x, plug it here, minus the second value of x, we should equal to 0. In this case, we have simple, or we have one integration at each step. So there is no propagation of the integration. Okay, so this was in computationally efficient, and we can use this one in real time. And for this one, we have all the states are equal to 0 based on the constraint that we have. Okay, second step, after we define the optimal nonlinear programming problem, now we would like to solve it. So we can solve this one using the what's called the IEEE optimizer, and this IEEE optimizer solved this equation and satisfied also the constraint to find the value of x, which is the decision variable. And for more information about this multiple shooting, single shooting, and the optimizer, I would recommend the workshop of our previous colleague Muhammad Mehrez, and this one is available on GitHub online. So now, once you have everything, once we have the decision like the optimal control sequence, let's come to the important question: does this control sequence stabilize the system? Sometimes yes, sometimes no, because we don't have any like criteria to evaluate this stability of the system, because it depends on the prediction horizon, sampling time, and also the model accuracy of the model and other kind of stuff. So we can't say like 100% this control is gonna stabilize the system. So in this case, we have to go further or in depth in the stability analysis or stability conditions of this controller. So to do the stability analysis or to guarantee the stability, the first step which is very popular in the literature, which is the stability guarantee using terminal conditions. So in this case, we have the running cost that we had before for all the assembly for all prediction horizon, and we add only one penalty condition or one penalty cost at only the final value. We would like to make sure that the final state converges with the reference value. So in this case, we have the terminal cost, and the minimization of this entire objective function should like follow or should make the objective function a Lyapunov function. Lyapunov function means the new value like minus the old value is less than 0. It means the value is the objective function or this cost function is decreasing with time, or this system is stable in the sense of Lyapunov stability. So in this case, like we have to find what the value of Qn and also define the terminal cost. So in this case, the terminal cost is the Lyapunov function, and the Qn is the solution of the algebraic Riccati equation. And using this equation, we have A and B are the linearized matrices of the system, and we have Q and R. Q and R are the weighting matrices of the running cost. So solving this equation, we can find the value of Qn that makes it to stabilize this system. The second solution for this stability guarantee is adding terminal conditions or adding terminal constraints. So terminal constraint, we force or we constrain the last value of the state at in prediction horizon n to be equal to the reference value. So this hard constraint, we force this one to equal the reference value. But the drawbacks of this techniques that like the solving the OCP or the optimal control problem using the terminal constraint is computationally expensive, because we have to satisfy this hard condition, so it's computationally expensive. And some other colleagues like recommended to use the invariant set. We can say that the final state just is within a invariant set, and if this happens, it means the state or the vehicle can converge like independently or automatically to the equilibrium coordinates. But still, this is computationally expensive. So also for the terminal cost, like terminal cost requires large prediction horizon to guarantee the stability using this terminal cost. So in any way, like both of them, like may degrade the performance in the system and also may degrade large computational cost, high computational cost and large prediction horizon. On the other hand, we can design the system as like the objective function without terminal conditions. We just had the running cost or the objective function that we had before, and our objective is to tailor an objective function for our system model or our system dynamics. And for this one, we can use like a specific or tailored objective function, and for this objective function we have the states and we have all the inputs. So for the states we have the position, velocity, and the angles, and for the inputs we have 3 inputs: thrust, commanded roll, and commanded pitch. And as I mentioned before, we can deal with the commanded yaw, psi, or the yaw angle as separate system, or separate state. So in this case, we have the penalty of the tracking error and penalty of the control input. And for the reference value of the input, which is specifically derived from the system model or the system dynamics. And here we have the tau and k of the system model, and also we have dz, which is the drag parameter in z direction. So this objective function is tailored for this model. And we did this one in order for make sure that the the value function, which is the infimum or the minimum of the objective function, is less than or bounded by this value. The value function is like stable or is a Lyapunov function and stable in sense of Lyapunov stability. So in this case, we have the initial condition and also we have a bounding sequence called gamma. So we have to tailor the system in order for us to find the sequence gamma. If we can find the sequence of bounding sequence gamma, it means we can guarantee this condition. It means we can guarantee that our system is asymptotically stable. So to find the value of gamma, it goes through like a long process or like derivation. So I would recommend reviewing our recent published paper. It explains in details how to find this bounding sequence. But by the end, like once we have the objective function and once we have the bounding sequence, we can see that we guarantee that the system is asymptotically stable. And also the power of this technique is that using this bounding sequence gamma, we can find what is the minimum or shortest prediction horizon that can guarantee the stability of the system. So in this case, we can find what the value of n that makes the alpha n greater than 0. And in our case, we find it to be n equals or greater than or equal to 4. So we guarantee that 4 stabilizes our system. Okay, so now let's go like a bit further to the implementation of the NPC in MATLAB. And in this one, as I mentioned, we are using CasADi. And for CasADi, we don't install it. We just download the package and insert it or import it to MATLAB. And then we define our system parameters. And then we define our control parameters. We define the sampling time, prediction horizon, and all the bounding or the weighting parameters, which are the Q and R matrices. And then we define our system variables, and in this case we are using something called SX symbols, which is the symbolic elements of matrices built in CasADi. In this case we define what is the states, we have all the values of the states, and also we define all the control inputs. And if we print the value of the states and the controls, we get symbolic vector that contains those variables. And then we, after that, we start inputting our system model, and once we have the value of the states or the variable of the system states and inputs, we can just calculate the rotation matrix, and then we calculate the position in world frame, which means we multiply the velocity in body frame times the rotation matrix to find the p of the position in world frame, and then we can insert our system model exactly as we had before in the equations, and we have those 9 states. Finally, we have seen that we have f function. This is our nonlinear system model, and this f function contains the states and the controls, and we have the system to follow this system dynamics. If we print the value of f, we end up with this function, that number of states, number of inputs, and the output will be 9 as well, which is the output of this function. And then with this function in our control design. Then we have the objective function. As we mentioned before, we have, if we are using the cost function without terminal cost, it means we have the running cost and we have the terminal cost. So in this case, we design the running cost for the entire n horizon. So we have a loop from 1 up to n, and for each loop we have like a vector called the x, which contains all the decision variables x, and vector called u, which contains all the decision variables u. So at each iteration, we take the decision variables x and u and calculate the value of the objective function as we showed before. And when k equals n, which is the terminal value, we add the terminal cost at this point using the qn. So now we have the symbolic expression of the objective function that we can use later. If we are using the proposed or the new cost function without terminal conditions, so in this case we have this running cost, and we apply it similarly as we did before, but without any terminal conditions applied to the system. After that, we have the discretization of the optimal control problem. So we to convert it to an LP or nonlinear programming problem, we use the multiple shooting. So for multiple shooting, we have the initial condition or the initial state, and then we apply. We have this is the initial state, and then we solve only doing one iteration, one integration, and then we subtract, and this value should equal to 0, and this will be the condition or the constraint applied to the optimal control problem. So for this one, we have this is the equality constraint that we applied, and this one for the upper and lower limit, so both equal 0, so it means equality constraint. Also, we can add some inequality constraint if we'd like to limit or constrain the control inputs. So we have the minimum and the maximum value of each control input that we have in the system, just in case we'd like to make it within desired level. After that, we start doing the optimizer. So with the optimizer, we have the decision variables. We have the x and u as decision variables since we are using multiple shooting. And here we have the nonlinear control problem. We have the objective function that we designed before, the condition variables that we have, and the constraint, the equality and inequality constraint, and also we have the reference values and initial condition. And then we define all the options for the controller, so optimizer, and we select iPuppet as the optimizer of the system. Finally, like we have the, if we print the value of the solver, we get this solver, we have the number of decision variables, and this value is relative to the number of prediction horizon. In our case, we have 20. So this number is relative to the number of prediction horizon. Also, we have the number of trajectory reference values, and this one is related to the number of the state. And we have upper and lower constraint. And the input output of this function is the optimized decision variables, optimized x and u, and also the value of the cost function, and also the value of the solution of the constraints. Then inside the simulation loop, we just at each iteration loop, like we have this while loop, we just call the solver to solve the problem at each time. So in this case, we have the update the reference trajectory at each iteration, update the initial condition or initial states coming from the feedback or the state estimator, and then we call the solver, we plug all the variables that we have, and then we end up with the optimal solution u, which is the solution of the system. And we need only the first element of this control sequence and apply this element to the user controller and do repeat this iteration iteratively. So to get to the simulation result, so in this case we have the numerical simulation. This is the proposed MPC or the proposed mean without terminal conditions, and in this case we have the n equals 20 and sample time is 0.1. As we can see on two different trajectories, our proposed one perfectly match or perfectly converge or track the reference trajectory. And also to study the powerful or the importance of this controller, we compare its performance to the traditional controller. Traditional MPC means MPC with terminal cost, and in this case we used n equals 4, which is the minimum value of the prediction horizon, and we decreased the sampling time, made it faster. And in this case, we can see that the blue one, which is our proposed controller, perfectly matched the trajectory. However, the red one, which is the traditional one, fails to match the controller. Also, to study the objective function, we did some hovering or some stabilization problems. They started from different starting point and hover at this end point. As we can see, all the objective function values or the value function all are monetically decreasing with time. It means our system is asymptotically stable. Then now let's go move forward to the real-time validation of the controller. So in this case, we designed the system using Python. So as I mentioned, the CasADi is compatible with Python and the MATLAB, and all the steps are exactly similar to the MATLAB, except the syntax of the coding. So in this one, we import the CasADi into the Python, and then we define our system variables, the states and control inputs, and also we input our system model, our system equation dynamics, and define the nonlinear function. And also we have the multiple shooting, as we did for the MATLAB. We do that similar to this one here to find the equality constraint, and then we define the equality equal this equality constraint to 0 for the optimal control problem. And also we design our solver using iPuppet, and then we solve this iteration iteratively and apply on the first control input going to the system. But in order for this one to work, we have to inject this Python code in a real-time or the real-time platform that can control the vehicle. And in this case, we are using ROS, which is Robot Operating System, which is a meta operating system that works on top of Ubuntu, and we can use this one to control the drone in real time. So in this case, to explain the idea of ROS, let's say that we have this drone and we have the camera in front of the drone. So if we can have the camera and the drone both separately, and in this case we have the controller running Ubuntu, and on Ubuntu we have ROS. So the camera is connected to the system, and also the drone connected to the system, and here the drones means the rotors. So first one, we have the the camera here, the camera generates images, so we can design like code a node, and we call it camera node. And this camera node subscribes to or takes all the images captured by the camera and publish it under a topic called image. So this one will keep publishing all the new images, whatever someone else will use it or not, but it will keep publishing under a topic called image. Then we have another computer vision node, and this node does some computer or image processing, and it takes any available image and subscribes to it and publishes the useful information from the image using a topic called blobs. Similarly, we have another topic called the blobs. Then we have the control node, and this control node takes the blobs, like does some estimation and do the control analysis. And by the end, we have the commanded thrust, and it published under the topic commanded thrust. And then we send this commanded thrust or subscribe to this commanded thrust and connect it to the vehicle and control the motor of the drone. After we set up all the connection, the ROS start to set up the communication, and all the nodes start to communicate with each other continuously. And this is for ROS 1. For ROS 2, it's a bit different, but in the same framework. So this is why we use the ROS, because for ROS we can build, divide the problem to different or separate nodes, and each node could be written in different language, like for Python, C++, or whatever its language, and just we have communication between each other using the published topics between them. So in our case, we designed here we had the ROS, computer running ROS, and for this one we had the algorithm of the NMPC controller, and then we had the trajectory generation node. It's another node that generates the required trajectory. And also, we have another node to subscribe to the cameras. So in this case, for our feedback, we are using OptiTrack cameras, and this OptiTrack cameras capture this for this volume, and the data goes to the computer running motive tracker software coming from with the cameras, and this one sends all the images to the ROS computer, and for this computer, it does some image processing to identify the position or the pose of the drone, which is the position and the orientation, and then since it's only pose, we need the velocity, so we have another node that can, which is Kalman filter, to estimate the velocity of the this vehicle. And we have in our lab, we have the drone here, and we have .r3 of the cameras that in the system. So now we can run our system and get the experimental results. As we can see here, a quick comparison between the proposed controller without terminal conditions and traditional controller with terminal conditions. If we have n equals 20 and the sampling time is 0.1, we can see both controllers work well, but the proposed one is still better than the traditional. And if we decrease the number of prediction horizon, we can see that both start to degrade the performance, but still the blue one or the proposed one is better than or beats the traditional controller. If we make our controller faster, it means we have the angular velocity of the rotation is higher, and also we decrease the sampling time. We can see that the traditional one completely failed because it's not designed for this small prediction horizon, but our controller is still rigid and still can follow the trajectory. And as we can see here, for different scenarios, we have different scenarios of prediction horizon and sampling time, we can see always the blue one, which is the proposed, the error range is always lower than the traditional one. Finally, let's go to the extension of this work. What happens, our system is, or our model is not accurate, it's not completely accurate. Of course, we have some unmodeled dynamics applied in the system, it changes in the mass, other direct forces or other forces, unmodeled forces. So how to include this in the system, or how to improve our controller, since it depends on the system model. So in this case, we are using the hybrid system, and this hybrid system contains the nominal model, which is the entire system that we had before, plus the unmodeled dynamics, we call it pi. And this pi in our case, it's unmodeled dynamics, and it contains the change in mass, which is constant, the rotor drag, because we already before had the rotor drag, but identifying the rotor drag coefficient is not easy. So in this case, we consider this as unknown or unmodeled dynamic. And also we had the fuselage drag force, which is nonlinear relationship with the velocity of the vehicle. So our objective is to how to learn or how to estimate the value of pi at each iteration based on the condition of the trajectory condition. So in this case, we will use the neural network or neural linear differential equation neural ODE. And for neural ODE, it's capable of, is powerful in estimation of the continuous function. Like if we have the input and the output, we can train this model to estimate the continuous function of the system, not just an instant point, but we can estimate the continuous function. So in this case, we can see that we have the our system. We have the this is the system dynamics. We have the states, initial states, and in this one we have the system dynamics. So in this system dynamics we have like the f hybrid, which is x and u, which are already like x is known and u is applied by the controller, so we can see it's known. The only unknown parameter is phi. So we have to learn this model, or we have to learn this neural network to identify the value of pi iteratively. So in this case, we can start with like guessing the initial value of pi, and then we solve for the this integration and solve for this problem to find what should be the next value of the state.
So we'll finish in 3 minutes.
Yeah, 2 minutes I'll finish.
Yeah, I'll be done.
So in this case, we have to find the like the next value of the state using the ODE solution, and also we have the actual value. We have the actual value, so using this loss function, we can find what is the difference between the predicted one and the actual one, and using this loss function to train the pi value. And in our problem here, we have the x will be the velocity of the system. Since we have this velocity at the pi, which is model dynamics, so we can implement the system to be exactly at this equation, and we can learn the value of pi. So in this case, for the value of the NMPC framework, before we had the exact value of the model, but we replaced this one with the trained model or the learned model. So in this case, we have the neural network that can identify or estimate the value of pi, and we inject it to the system model to do the system prediction using the system model. And model dynamics. It means our system now is aware of any model dynamics applied on the system, and then we use it to calculate the error, do the optimization, and inside the optimization we have the input constraint. Also we have the cost function that's also aware of the value of the model dynamics, and then we generate the first control signal, and we use this control signal with the feedback to do the next estimation of the model dynamics and apply it in the system. So we have quick results from our work before. So for this one, we have 4 controllers. So this is the proposed MPC, our proposed one, but we have the capability to estimate the model dynamics using the neural network. This traditional controller will terminal costs, but also it's aware to identify this learning the system model dynamics. And also we have the proposed and traditional controller without the capability of identifying any model dynamics. So in this case, we can see that the 4 controllers, the proposed neural ODE one is the best for all the controllers for this trajectory control problem. As we can see that the blue one converges with the trajectory tracking. However, the others fail, especially at lower prediction horizon. The same for different shape of the trajectory. We can see that the proposed one still beats all the other controllers. And that's it. And thank you for joining. Any questions?
So in the interest of time, we'll answer the questions downstairs. Okay. So thank you for the presentation, Hakim, and I got it recorded. So if you don't mind, we'll use this recording, let's say.
Okay.
We'll like to distribute some places. So we'll meet you downstairs and have the questions.
Okay. Thank you. Thanks.